All right, let's dive a little deeper into the photoelectric effect and consider the experiment which sought to either refute or prove Einstein's explanation of the photoelectric effect. So let's talk about the setup of the experiment. First of all, there was really three variables that the experimenter could change. One is the light source intensity. Um, In other words, the brightness of the lamp or the brightness of the bulb that was used. The next thing we could change in the experiment was the frequency or wavelength, aka the color of the light that was being used. And finally, we could change the what's referred to as the photoelectric surface or the metal that we are going to shine the light on. So those are the three things that the experimenter could vary in the experiment. To be clear, using the term light here, but as you will see, we will use different parts of the electromagnetic spectrum in order to initiate the photoelectric effect. All right, so I have here a little simulation that allows to demonstrate the photoelectric effect in a way that you can see the impact of each of the different variables. So just to go through this again, I have the light source intensity. I can vary the light from very dark to very bright. I'm just going to dial it right up to 100 for the rest of this simulation to start with. Light frequency or wavelength, I can start way down here in the infrared. Wavelengths and frequencies go into red, yellow, green, blue, indigo, violet, etc., and even get into the ultraviolet. And then we can change the photoelectric surface. That's the photoelectric surface here. I can go from sodium and let's just do the classic zinc. So those are the things that we can vary in this experiment. Now, in addition to what we can deal with in terms of the variables, there's also what are we actually trying to measure here? And really, there was a trick, and that was trying to do direct measurements of the photoelectrons in order to draw conclusions or deductions about the photons. Let me show you what I mean. In the experiment, we can measure the current, also called the photocurrent. You get a theme going on here at the photoelectric effect. I like to drop photo in front of every one of the words. But we could measure the current of the electron. So we can measure the emitted photoelectron current in amperes. Why would we do that? Well, we want to deduce from this the number of electrons that are coming off the plate, because we can directly do that. Remember, if we can get it in coulombs per second, we can quickly convert that to electrons per second. And the question was, can we trace that back to the number of photons? If Einstein is right, they will be equal. The number of electrons coming off should equate to the number of photons. So if photocurrent goes up, that means that the number of electrons coming off is going up, and we can work that back and deduce that the number of photons is going up. The other quantity that we keep track of in this experiment is something called the stopping voltage, and I'll demonstrate that when we get back to this. But basically, the stopping voltage is the amount of voltage needed to stop the most energetic of the photoelectrons. So picture this, electrons come off the surface, and then we apply a voltage to try to stop them. Hence the term stopping voltage. Why do we do that? Once we know the stopping voltage, we can use the stopping voltage to find the kinetic energy of the photoelectrons. All right, so again, the game is what we learn about the photoelectrons can lead us to deductions about the photons. So if the electrons have more energy, we can work back to find out the energy of the photons. To be clear though, if we find the kinetic energy of the photoelectrons, in this case, it's not going to be the same. So this will all become clear as we go through, and you can go back and forth and look at these statements to make sure they're consistent when we're done. But in the end, we have three variables that we can play around with, but two things that we're going to keep track of: the photocurrent, aka the number of electrons, which we expect to be the same as the number of photons, And number two, the stopping voltage, which is not exactly, well, which will lead us to not exactly equal to the kinetic energy of the electrons. And that will lead us to draw some conclusions about the energy of the photons. But again, these things aren't necessarily equal at this point. So let's get back to our experiment. So I've got it dialed up to 100%, and let's take a look at what happens. First of all, with the most interesting thing from the photoelectric effect is what is really going on when we change the wavelength or frequency or color, all synonymous. And you'll notice that as I go from infrared to red, nothing really happening at this point. Dial up higher and higher, eventually get into yellow, still nothing, even into the blue and violet. But there's going to be some point at which the frequency and wavelength is right, and we start to get these electrons emitted from the photoelectric surface. So you'll see these. You have the benefit of seeing this in an animation. You can see the electrons coming off. In the real life experiment, we would only be measuring or reading the current. It's only when we see a current that we know electrons are coming across. But again, you get this cartoon version of the photoelectric effect experiment where we can amazingly see these super small electrons coming off the plate, as well as see the current going up. And as I increase the frequency and decrease the wavelength of the light, you can see what impact that has on the electrons. They have more and more energy. No surprise, this is what Einstein predicted, that as we change the wavelength and frequency of light, we're actually changing the energy of the light. And that means that the energy of the electrons can be greater when the energy of the photon is greater. Now I'm going to do something with this simulation again that we can't do in real life. We're going to look at this as photons, and now you can see instead of this light giving off just this indescript light, we can now see it broken into photons, and now you can get a better sense of what Einstein was imagining with his great mind. It was these individual photons coming in. Each one is just this bundle of energy that can then hit the target and emit electrons. So let's go back down to the different colors. And as I dial it up to red, you can see all these photons, same number of photons, they're hitting the plate. There's just nothing happening until we have enough energy to break those electrons free. Then as I increase my frequency, increase the energy of my photon, I get higher and higher energy of my emitted electrons. All right, so watch what happens when we have enough energy of the photons to get the photoelectric effect. Let's see what happens now when we change the brightness. So let's go from 100 down to, say, 50%. And you can see, obviously, what's happening with the number of photons is that has been reduced. And as a consequence, if there's less photons hitting the plate, we get less electrons coming off. So again, if I dial this down to like 20%, not that the energy is any different. Each of these electrons still comes off with a lot of energy. Let's just look at the highest energy ones. It's not the amount of energy that's really changing. It is the number of electrons that changes. So you can see this phenomenon that Einstein predicted pretty clearly in this simulation. The wavelength and frequency really is determining the energy of the electrons, therefore the energy of the photons. The intensity of the light source really is the number of photons. And what's the role of the photoelectric surface? Well, it turns out that certain metals, they just love their electrons more than others. So zinc, you can see we needed somewhere in the UV to get some electrons away from zinc. If you replace your zinc with some sodium, you expect maybe you have to put in more or less effort, more or less energy from your photons to get the electrons off the plate. If you want something that really loves its electrons, check out platinum. UV, you got to get way into the beyond UV, almost X-rays, in order to get electrons off of the platinum. So just revisiting this idea then, we're looking at photocurrent as the measurement of the number of electrons and the number of photons. Stopping voltage is something that measures the energy of the electrons. Let's go back and take a look at what the stopping voltage does then. So let's get some photoelectric effect happening. Let's just shoot really bright light with really high frequency at the plate, and we can see when we shine this ultraviolet light on the zinc plate, we get the photoelectric effect. And so let's see what happens when I start applying a voltage. And so you should understand that a voltage is a potential difference, and it could either encourage these things to go faster, or it could discourage them from going faster. It can make them go slower. So I'm going to put the polarity such that I'm going to apply a voltage where this plate on the right is negative, this plate on the left is positive, and you can see what's happening. I'm starting to stop some of the electrons that are coming off the plate, but clearly I'm still getting a current, so I haven't stopped all of them. Stopping voltage by definition is what is the minimum voltage to stop even the most energetic of these electrons. So 1.4 volts doesn't quite do it. 1.8, I can see I get dropped to 0, but 1.6, I still get a bit of a current. I can type in some smaller numbers, but somewhere between 1.6 and 1.8, we get our stopping voltage. And we'd have to investigate a little closer to see exactly what it is, but the stopping voltage might be around 1.7 volts for this. In other words, I need to remove 1.7 electron volts worth of energy in order to stop the most energetic of these photoelectrons. If I change the wavelength of light to something with a higher frequency, now I get a current again. So I need to apply more stopping voltage. And Einstein says this is exactly what you should expect. If you increase the frequency of your light, you are increasing the energy of the light. We know that now from the experiment because we have to increase the stopping voltage to stop the electrons. I want to emphasize the game we are playing here. In a real life experiment, we don't see photons, we don't see electrons, we measure photocurrent, and then we work our way back to what's going on. We measure stopping voltage, then we try to deduce what that really means for the electrons, and therefore what that means for the photons. And so that's the game people played when they did this experiment to convince the world that Einstein was indeed right. So here are the results of this. Number one, let's take a look at what this meant in terms of frequency of light. We saw that as the frequency of light was increased, the energy of the emitted photoelectrons was also increased. And we saw that if you were doing the real life experiment, you saw that because of the stopping voltage. The most classic representation of this is a graph that you will see again, and that is one where on the y-axis we get the kinetic energy of the electrons. So the electrons' kinetic energy on the y-axis, and on the x-axis we have the frequency of the photons that we shot at the metal surface. Now, I'll just fill it in. If we started way down here with low frequency light and a zinc plate, then we get no photoelectric effect, so we get no energy of the electrons. And then we dial it up from red to orange to green to, you know the order, red, orange, blue, yellow, green, indigo, violet, whatever it is. Nothing, nothing, nothing. So no kinetic energy of the electrons. This is my green line here is really what you would see if you produce this graph. Then we hit this certain point, and you'll hear this term starting now. It's called threshold frequency, aptly named because it is the threshold between no photoelectric effect before it, but after that threshold frequency, the graph starts to take off like this. And so you can see what's happening is now we're getting the photoelectric effect, and now as we increase the frequency, UV, higher UV, X-rays, gamma rays, all that, we always get the photoelectric effect. We are just increasing the kinetic energy of the electrons as we increase the frequency. So this green graph line that I've drawn is the real life experiment. In this graph, they have extended this line down here, and we can talk about that at some point. But the conclusions are really this. Yes, indeed, the photon energy is h times the frequency. We can see that happening here. We also have another conclusion here, and I'm going to introduce another term. So where we have threshold frequency here, we also have another term called work function. And the work function is really the work necessary or the work needed to get electrons freed from the surface. So you imagine that these electrons are embedded in this surface of the metal, and they don't really want to leave. But if you put in enough effort, aka the work function, if you overcome the work function, we say, then you can free the electron. And the work function, if you understand this graph, go back and look, the work function can be found if you multiply Planck's constant times the threshold frequency. So this F naught is referred to as the threshold frequency, and the threshold frequency allows us to find the amount of work, the minimum amount of work, the minimum amount of energy we need to put into a metal surface just to free the electrons. After that, not only do we free the electrons, we also get a bunch of kinetic energy out of them. So on the one hand, we learned a little bit about the frequency and its relationship to the energy of the photon. And there's some math coming, so we got some equations to deal with. The second big conclusion that's relevant to us is the intensity of the light, as you increase it, so does the photocurrent. And so basically, you can imagine this, and this is what Einstein predicted. If you shoot a single photon at a metal surface, as long as that photon had enough energy, it will emit a single electron. There's this one-to-one interaction. Now, makes sense then that if we shoot a second electron, so instead of just one photon, we brighten the bulb a little bit. Now we have two photons. Now we get two electrons, and the argument continues on. Shoot three photons with enough frequency, enough energy, they will free up three electrons. So we make this logical conclusion, even though we're never dealing with one, two, three, we're dealing with bajillions of different photons and electrons. The number of photons hitting the metal is equal to the number of electrons emitted. This isn't an ideal world, by the way. If you go back and watch the simulation in the real world, it's not quite as pretty, but for our purposes, as we start learning this, we're going to make the assumption that the number of photons hitting the metal will equal the number of electrons emitted, or at least if you want to think of it this way, the maximum number of electrons that could be emitted. So if we shoot 1,000 photons, we could get 1,000 electrons off. In real life, you might not get all 1,000. If you want to look into that a little more, go ahead. But for now, you might see questions that say, what's the maximum number of electrons that could come off? They're really just saying if there's this ideal one-to-one relationship. Okay, that brings us to the money slide, and that is the math of the photoelectric effect experiment. If you go back and look and watch it enough times, you'll start to understand the idea and the principles around the photoelectric effect experiment, the variables and the outcomes, and ultimately leads you to the same path. Mathematically, to analyze the photoelectric effect experiment, it comes down to the granddaddy of all physics formulas or physics concepts. This one here, the initial energy that you start with equals the final energy, also known as the law of conservation of energy. You may have heard of it. And that's what this really is. On the one part, we have the energy of a photon coming in and hitting a metal plate. So as that photon hits the metal surface, then the energy gets converted into two possible forms. One is the work function. That is the energy it takes just to free the electron to the surface. Then, if we have enough for the work function, we may also have enough remaining for the kinetic energy of the electron. So the picture in your brain that you can have is We have a surface here, and inside the surface we have an electron. And the electron is going to get hit by some frequency of light. Red light, low frequency, very little energy. Imagine this red light hits this surface, and it's not enough energy to bubble this electron to the surface. So we get no photoelectric effect. So scrap the red light, let's turn it into something with a little higher frequency. For example, violet or blue light. So now we shine our violet light photon at the surface, and imagine that there is another electron sitting here. And now the violet light has enough energy to overcome this work function. So I did this squiggly little line to represent my W, my work function. So because this photon has enough energy to overcome the work function, the electron may also come off with a certain amount of kinetic energy. So our initial energy is way over here. It was the energy of the photon equal to h times f. That's the initial energy. So I've written this here. So if you break this law of conservation of energy into the formulas for each of these forms of energy, there's my initial energy, my frequency times Planck's constant, the energy of the incoming photon. Then that energy gets turned into two possible things. Work function, gotta get the electron free to the surface. If we don't, then nothing's happening. And that's h times f naught, we say. So the low frequency, the threshold frequency. And then if it comes off in the experiment, the kinetic energy of the electron could be found using QV stop. We've seen this formula before. If you go back to previous studies in electric forces and fields, there was a formula that says the voltage is equal to the change in energy over the charge. So I've just rearranged that and put it in here. The electron energy is removed using the stopping voltage. So this formula is really the kinetic energy formula for the photoelectric effect experiment. It's the energy of the emitted photoelectron. So this complete formula is not at your fingertips, but you can certainly build it understanding the experiment, where the incoming energy of the photon that we're hitting the plate with turns into these two kinds of energy. The energy to overcome the work function, that we got to get this thing to the surface first of all, and then anything over and above that turns into electron energy. So I want to finish this presentation off with this kind of simplified version, but I think it's really kind of telling and ties in well with the formulas. Kind of this little diagram showing some possible numbers we can use. So imagine then that we take red light and we shine it onto a potassium surface. Now potassium, it turns out, we need 2 electron volts just to free the electrons. So the work function, we would say, for potassium is 2 electron volts. So imagine we shine in red light with its 700 nanometers, its measly 1.77 electron volts of energy. That photon is not got enough energy to free the electron, can't eject the electron, so we don't get the photoelectric effect with that red light. If we dial up the light to green light, now green light's got a shorter wavelength, a higher frequency, and this particular green light has 2.25 electron volts worth of energy, much more than the red. So when it hits the surface, it has enough to overcome the work function. It has enough to free the electron to the surface. And it has enough not only to do that, but it's got an extra amount of energy to give this emitted electron some velocity. Now, you can prove this to yourself, but if you've been paying attention, if we had an initial energy of 2.25 electron volts, it took 2 electron volts to free the electron, then how much energy does this have, this electron, in the form of kinetic energy? Well, simple math will tell you it's got 0.25 electron volts worth of energy. So 2 of the 2.5 that we started with went to pay for the work function. The remaining 0.25 electron volts is the kinetic energy. If we dial up the frequency even more, make this thing a shorter wavelength yet, and use like some sort of purple light here with its 3.1 electron volts, well, 3.1 electron volts is our initial energy. That should equal the work function plus the kinetic energy of this material, or this electron that came off. So if we went in with 3.1 and it took 2.0 electron volts just to free it from the surface, then again, we can see that we have an extra 1.1 electron volts. That 1.1 electron volts corresponds to the kinetic energy. By the way, I don't think this is going to shock too many people, but to get this velocity, it's related to the kinetic energy, 1/2 mv squared. So in the experiment, we said we can find the kinetic energy using Q times V stop, but that doesn't change the fact that any particle with mass and velocity has a kinetic energy equal to 1/2 mv squared. So you can see a number of relationships starting here. But take a look at this slide. I think it's really kind of uses some nice numbers that you can wrap your brain around and do the math without a whole bunch of calculations. And you can start to put together this idea of how the incoming photon energy ends up being a combination of work function that needs to get paid first of all, and then kinetic energy. If you can't pay for the work function, then that's the end of the experiment. The light hits the surface and either reflects or gets absorbed some other how and increases the thermal energy, but it will not produce the photoelectric effect. Oh, final thing. You might be asking yourself, in the end, we have this electron coming off with all of this kinetic energy, all of this speed. What happens to the photon over here? Well, why don't you ask yourself, what happens when you take something which is not a form of matter? There's no atoms or molecules making up this photon. It is light. It is a bundle of energy. What happens when your bundle of energy no longer has any energy? What happens when we take away 2.25 electron volts from something that is nothing but energy? And the answer is, it becomes nothing. So take the energy away from the photon and it becomes nothing. So there's no evidence of the photon later on. There's no reflection or anything happening. The energy is gone, and it's found now in the form of this emitted photoelectron's work function and its kinetic energy. All right, so lots of stuff here. I'm not going to do a single calculation in this presentation. I will save the calculations for separate bite-sized piece presentations, but please feel free to go back and look at this. If you can find a simulation online like the one I was playing with, it might help you to conceptualize what's going on in the photoelectric effect experiment. A lot of terminology and a lot of things that are happening. Initially, we're focused on the effect of frequency and intensity and what that means in terms of light. Frequency is related to the energy. Intensity is the number of electrons or the number of photons. So keep that in mind as we move forward.